Welcome. In the previous session when we were talking about constraint handling, so we only discussed on penalty approach, right. So, as and when a meta-heuristic techniques provides a solution, we check for the constraints, right. If the constraints are not satisfied, we assign an appropriate penalty, right. So, the penalty can be either hard penalty or it can be determined based on the amount of violation, right. So, previously we had solved production planning problem using this approach, wherein we had used a hard penalty approach for handling the domain constraint, right. So, any solution which gave a production which is non-zero, but it is less than L, we penalized that solution with a constant value of 10 power 5, right. Whereas for budget and investment constraint, we determined what is the extent of violation and we assigned a penalty appropriately. Another way to handle constraint is to correct the solution, right. So, based on the nature of the problem, whatever solution we receive from the algorithm can be corrected, right, based on the domain specific knowledge, right, and the corrected solution can be returned back to the meta-heuristic technique, right. So, it is a very simple approach. That approach can provide significant improvement in the results, right. So, that is the approach we will be looking in this session, right, and we will demonstrate it on the production planning problem, so that you can realize the benefit of employing a correction approach rather than a penalty approach. If you recollect whatever we have been discussing so far, this was the communication between the meta-heuristic technique and the optimization problem which we had, right. So, the meta-heuristic technique will pass the solution X to the optimization problem, and the optimization problem in turn will provide the fitness function of this X, right. If this X is an infeasible solution and if we are solving a minimization problem, this F would be a very high value, right. Whereas in the correction approach, what we do is the meta-heuristic technique still passes the solution X, right. The optimization problem does not merely determine the fitness function of X, right, but checks for the violation, and if there are any violation in any of those constraints, right, if there is an inbuilt mechanism, right. So, if we employ some mechanism, right, which will help to improve this solution X, right, then that improved solution is passed back to the algorithm. Along with the improved solution, we also pass the fitness function of the improved solution, right. So, it is not correct to convert X to XC. Let us consider we have a 2 variable problem and the decision variable passed are 2 and 3, and let us say there is a mechanism in the optimization problem which looks into the solution and corrects the solution to 2 0, right, and the fitness function of this 2 0 is let us say 16, right. For some evaluation of the objective function and the other constraints, the fitness function value turns out to be 16, and for this 2 and 3 let us say it is 25, right. So, what we obtain from the algorithm is 2 3, it has a fitness of 25 and it violates some constraint, right. There is some mechanism in this fitness function which corrects this solution, right. The solution is corrected to 2 0 and the fitness function of this 2 0 is let us say it is 16. The solution is better than this solution, and this betterment is not directly because of the meta-heuristic technique, but because of the mechanism which we had employed over here to correct the solution, right. So, in this case what the optimization problem is supposed to communicate to the meta-heuristic technique is not the value 16, but also the solution 2 and 0, right. So, what should happen in this meta-heuristic technique is this 2 and 3 should be replaced with this 2 and 0 and the corresponding fitness function value, right. So, this is the correction approach wherein we get a solution from the meta-heuristic technique, we employ some mechanism which is problem specific, right, to correct the solution, and we send back the corrected solution, in this case 2 0, along with the fitness function value of the corrected solution, right. So, for example, if we consider teaching learning based optimization, we generate a new solution, that new solution let us say it is 2 3. So, when it is communicated to the optimization problem corrects it to 2 0, and this 2 0 is sent back to the meta-heuristic technique along with the fitness function value of 16. So, the meta-heuristic technique or TLBO in this case should consider 2 0 as the newly generated solution along with its fitness function. So, it is this solution which has to be now used for greedy selection, right. So, this correction approach, as you can see, it is a very straightforward approach. Only thing is that we should be able to develop a mechanism for the problem at hand, right. So, it is very problem specific. The correction approach is not part of the meta-heuristic technique, but it is a part of the optimization problem. but it is implemented in the fitness function evaluation, right. There are a couple of things which you need to remember while employing a correction approach, right. The first thing is that the fitness function should be calculated for the corrected solution, right. So what we get from the algorithm is the set of decision variable, let us call it as x, right. So that is corrected to a new solution, let us say xc, right. So penalty is not supposed to be calculated for this x, right. So penalty is supposed to be calculated after correcting the solution. This is because when we are conveying the fitness function value, right, we should convey the fitness function value of the solution which we are passing to the algorithm. So the solution that which we are passing to the algorithm is xc, right. So the fitness function should correspond to this corrected solution, right. So for corrected solution, if you think about it, at least for this production planning problem, if you see that it will not have any violation of domain constraint, right. So this will have a better fitness than x, right. So there is no need to calculate the fitness function of x itself, right, because we are anyway correcting the solution. Once we correct the solution, we can find out the penalty for that, right. So in this case there won't be any violation with respect to domain constraint, but there may be violation with respect to raw material 1, raw material 2 and the budget constraint. So the penalty is to be calculated for the corrected solution, and then fitness function is to be calculated for the corrected solution, because this is the solution which we are conveying back to the meta-heuristic technique plus penalty of the corrected solution. So this will be the fitness which we need to pass through the algorithm. So here you need to remember that whenever we are employing a correction approach, we are doing something on top of what the algorithm is doing. So the algorithm, let us say it suggested a solution 1, 2, 3, right. So for some reason we are correcting that solution in the optimization algorithm. Let us say that solution 1, 2, 3 becomes 3, 8, 7, right. So we have done something on top of the algorithm. So in some sense you can say that we are disturbing the algorithm. For many problems, depending upon the correction approach that you employ, you may get a better result, but there may be cases wherein a correction approach does not enable you to get a better solution. So in the case of production planning problem, so this was L, this was H, right, and let us say M. Let us say L is 50, M is 100 and H is let us say 175, and this 0 is a feasible solution, right. So if we get any solution over here, right, it does not violate domain constraint, so we were not adding penalty. If the solution is here, we again do not add any penalty, right, or if the solution is 0, we do not add penalty. So what we were doing previously is that if any solution was over here which is greater than 0 but less than 50, let us say it was 45, right. So what we did for this solution 45 is that we assigned a penalty for it, right. So instead of assigning penalty, what we can do as part of the correction approach for production planning problem is that any solution which is greater than 0 but less than L can be converted to 0, right. So this is a mechanism that we are employing, right. So solution x remains x, right, if this x is greater than or equal to L and less than or equal to H, remains x if x is 0, right. And what we are saying is we will convert it to 0. The algorithm gave us some value, but we will convert it to 0 if this x is greater than 0 and it is less than L, right. So this is the correction approach that we are employing, right. So we will correct the x and we will no longer assign the penalty, because we have converted the solution in such a way that it no longer violates the domain constraint. So we will no longer penalize it, right. So to better understand, let us consider an example. Let us look into the production planning data. Now that we have designed a correction approach, we can implement that. So this fitness function will receive the solution x, but it will return not only f, but it will also return the corrected solution, right. Okay, so this is done. We are no longer going to have any variable which is going to violate the domain constraint, right, because we are going to correct it, right. So if x lies between L and M, we do not need to do anything because no penalty was calculated. If x lies between M and H, again we do not do anything because it was already in a domain, right. So previously what we had done was, if a solution is greater than 0, right, and less than L, we were assigning a penalty. So right now what we will do is, we will not assign a penalty, but we will merely correct the solution, right. So we will say x of j is equal to 0, right. So no matter where the solution lies, right, if it is greater than 0 but less than L, it does not satisfy the constraint. since it does not satisfy the constraint, previously we were assigning a penalty, now we will not assign a penalty, but we will merely correct the variable. So, the corrected value of the variable is 0, because 0 we know for sure does not violate the domain constraint, right. So, we assign it to 0. As discussed earlier, right, you can also assign it the value of L. As discussed earlier, you could even choose it to assign it a value of L, right, or you can generate a random number and see if the random number is greater than 0.5, you can assign it to 0, if it is less than 0.5, you can assign it to L, right. So, here we are demonstrating one of the scheme, you can try out the other two schemes, right. So, this x of j is equal to 0, we do not need to change anything with respect to calculating the investment cost or the raw material requirement of 1 and 2, right. So, everything will remain same, except that this term is no longer needed, because there is no penalty with respect to violation of the domain constraint, because if any solution violated the domain constraint, we corrected it, right. So, over here we have removed that thing, right. So, now our objective function is compatible, but if you look at our algorithms were designed in such a way that it can receive only the fitness function, right. So, what we will do is we will make a copy of this, so that we can compare both the approaches, right. So, let me say this is TLBO correction, right, and over here we will receive not only the fitness function, but we will also replace the member which we sent, right. So, the member which we are sending is the pth row of the population, right. So, that we are replacing with the solution provided by the problem, right. So, this line has become compatible now, right. In two other places we would be calling the objective function, one is after generating the new solution in teacher phase, right. So, over here, so here we will say f new comma x new, right. So, we now receive not only the fitness function, but also the corrected solution, right. So, if the solution is already within the domain, nothing is going to change, right, we will not be modifying, the correction approach does not help, but if the solution is violating the domain constraint, it is corrected in such a way that the solution no longer violates the domain constraint, right. So, similarly over here f new comma x new, right. So, this we have converted for TLBO, right. Similarly, let us convert for differential evolution, right. So, this is differential evolution, it employs correction approach, right. So, remember we are able to do this because we have complete control over the algorithm as well as the problem, right. So, since the algorithms we had coded it ourselves, since we know this algorithms, we can employ this correction approach, we can easily employ this correction approach. So, over here we are again receiving the pth member of the population, right, and then we will be evaluating the objective function over here, right. So, the solution which we are sending is the jth row of the variable u, right. So, what we will get back is another solution. So, the newly obtained solution is plugged in the same position, right. So, this we have done for differential evolution. So, differential evolution we call the objective function only twice, once is for the initial population and then once when we have calculated all the solutions, right. So, this is inside a loop. So, that way we are calling it NP times. For particle swarm optimization also we will be calling it only twice, one is during the initial phase. So, we need to make a copy of this. So, now here we will have the new solution. Similarly, we will be using the objective function over here, right. So, over here also it is the pth member of all columns. So, with these three files, right, TLBO correction, differential evolution correction, PSO correction, we have converted the algorithm such that it is compatible to be used with a correction approach, right. So, let us go back to this, right, we will repeat this so that we can compare the correction approach and the original approach, right. So, here we need to call this correction. So, this correction has to be given over here, right, and again over here, right. So, let me use another variable for this thing, best fitness C, right, and similarly let me define this over here, right. So, this best fitness will give us the performance of the algorithms without correction, whereas best fitness C would give us the performance of the algorithm with correction. We can also repeat these lines, right. So, let me use this variable. So, again this is a bit crude way of doing it. If you have sufficient coding skills, you can do this same thing in a much better way, right. So, now what we are doing is we are solving the same production planning problem with 3 different algorithms: TLBO, differential evolution and particle swarm optimization, with correction and without correction, right. So, these are without correction. So, the first 3 are without correction, the last 3 are with correction, right. So, the fitness function also we need to have it in 2 forms, right. So, one is prob, another one is prob C. So, one employs correction, another one does not employ correction, right. So, for those functions which do not employ corrections, we do not need to make any changes. Wherever we are employing correction, we need to pass the appropriate file, right. And then this production planning we need to have as production planning C, right. So, this is production planning correction approach, right. So, for without correction we will have this, only f is returned, right, without correction, right. And right, so this line would be active, right. So, this is to be converted plus sum of penalty underscore domain, and we can also uncomment this line, right. So, what we have now is 2 objective function file, one employs the correction approach, right, f comma x, right, the other one returns only the fitness function value f, right. Over here in this SKS underscore production planning C, we employ the correction approach, right, no penalty is being assigned and the variable value is converted to 0, and that set of modified decision variable is passed back to the algorithm, and we do not have any penalty over here, right. Whereas this production planning is the same file which we have been using in the previous session, right. So, we assign a penalty over here and we add the penalty, right. So, this is the violation with respect to every decision variable, we sum it up and add it to total fitness function, right. So, now if we execute this, let us see if we are able to execute it without any error. So, now let us look at both the variables stat and stat C, right. So, remember stat and stat C are identical in nature, right. Only difference is for stat we did not employ a correction approach, for stat C we employed a correction approach. So, this has to be best fitness C, so now if we execute this, so we can have a look at the variable stat, right, stat C. Remember the nature of stat and stat C is the same, right. So, each row indicates an algorithm, the first column indicates the best value determined by the algorithm, the second column indicates the worst value, the third one mean, fourth one median, and the fifth one is standard deviation. The first row is for TLBO, second row is for differential evolution, and the third row is for particle sum optimization. So, stat is the same set of results which we would have obtained previous, right. Whereas stat C, the columns are the same, the rows are the same, only in this case we employed a correction approach, right. Now, if you see the best value reported by TLBO, right, was minus 400.59 without correction approach, whereas with correction approach it gives a value minus 699.38, which is significantly better, right. Even the best solution was not feasible, right. Here now it is able to find a solution which is minus 690.82. Particle swarm optimization was previously able to determine a solution of minus 546.28, now is able to determine a solution of minus 710, right. So, if you think about it, we employed a very simple procedure, right, but that simple procedure has helped us to get significantly better result, right. So, even if the standard deviation also has considerably dropped, right. So, from 31.18 and 98.61 it has dropped to 20.45 and 62.19, right. That is the benefit of correction approach, right? So again we need to remember that the correction approach is very problem specific, right? So for this problem, pushing the variable to a value of 0 helped us to satisfy the domain constraint, right? So it's not necessary that the same correction procedure will work in all problems. It is very problem specific. That is why we chose to include that correction mechanism in the fitness function evaluation file and not in the algorithm as such, right? We could have even implemented it over there, but then that may or may not work for all problems, right? But the correction approach usually is expected to give better results, right, than an approach without correction. So in this case we did not assign any penalty, but we helped the algorithm by correcting the solution. So we need to remember that when we correct a solution, we not only should pass the objective function value, but should also pass the corrected solution. That is one of the correction approach, right? So you can also think of other approaches, right? So for example, let us assume this is the low level capacity, this is coming from the data, right? So it's more like we cannot produce anything less than 5, we cannot produce anything less than 9 for second process, we cannot produce anything less than 1, right? We cannot produce anything less than 3 for process 4, and we cannot produce less than 4 for process 5. Again 0 is allowed, right? So if there is a 0, that is not an issue, right? So let us assume that this is the decision variable that we are getting from a meta-heuristic technique, right? Let us say we get 12, 6, 2, 19, 2, right? These two values are non-zero, but they are also lower than the respective L value, right? So this is the approach which we discussed, right? So for all those variables which do not satisfy the domain constraint, right, we will assign it a value of 0. So this is the approach which we discussed earlier. So here what we are doing is, if it is not equal to 0 and if it is less than L, we are assigning a value of 0, else we retain the value of xi as given by the meta-heuristic technique. So for example, here the value given by meta-heuristic technique is 12, 2 and 19. So we are not modifying those values, right? Those values satisfy the domain constraint. So we do not change them, only those things which violate the domain constraint we change it to 0, right? So the other approach could be fixing it to low level, right? So in this case what we are doing is, if the value is within the domain, then it is fine, right? Otherwise if it is less than L and if it is non-zero, we make it as L, right? So for example, this variable was violating, the 6 and 2 are violating. So right now what we do is, this 6 will be converted to 9, so this is 9, right, because the low level value is 9. Previously in this first approach we converted it to 0, here we will convert it into 9, right? Whereas for the fifth variable, the value that we get from the meta-heuristic technique is 2, right, but the L value is 4. So here we fix it to 4, right. So this is another approach. So we can either employ this approach or we can either employ this approach. So there is also another approach wherein we fix it randomly, right. So here we generate a random number for every decision variable that is violating the domain constraint. If the random number generated is less than or equal to 0.5, we fix it to 0. If the random number is greater than 0.5, we fix it to corresponding Li values, right. Otherwise if it is in the proper domain, we do not need to change it. So for example, consider the second process, right. So the low level value is 9, the value that we get is 6, right. So if we generate a random number and let us say the random number happens to be 0.3, right. So if r is less than or equal to 0.5, so 0.3 is less than or equal to 0.5, so we fix it to 0, right. Similarly if we see the fifth variable, r is 0.8, right. So 0.8 is greater than 0.5, so we fix it to its low level value. So this 2 gets converted into, so what we got from the algorithm is 12, 6, 2, 19 and 2. What we will be returning back is one of these three, right, either 12, 0, 2, 19, 0 or 12, 9, 2, 19, 4 or 12, 0, 2, 19, 4, depending upon which approach we take. So over here we will demonstrate the approach 1, right, we will implement it on the codes that we have. You can evaluate both of these approaches, right, or design your own approach to see if you are able to get better results than what we are discussing over here. Now the question can be, why did we correct only for the domain constraint, why not for raw material constraint or the investment cost constraint? If you can design a correction mechanism for investment cost as well as raw material constraint, you can implement it. So if you are able to design a correction mechanism to handle investment cost and raw material constraint, you can even choose to implement it and check if it is actually benefiting the algorithm. In the previous session, we had seen solution of the production planning problem using teaching learning based optimization. We did not compare it with other algorithms, right. So, first what we will do is we will solve the same problem, right, with particle swarm optimization and differential evolution along with TLBO, right. So, out of the 5 techniques which we have discussed in this course, out of the 5 techniques which we discussed in this course, we are selecting only 3, right. So, particle swarm optimization, teaching learning based optimization and differential evolution. The reason for doing this is that for these 3 algorithms, the maximum number of functional evaluation is a deterministic expression, right. So, for example, for teaching learning based optimization, it was NP plus 2 NPT, right, where NP was the population size and T was number of iterations. For particle swarm optimization and differential evolution, the expression, if you remember, it is NP plus NPT. This is because in teaching learning based optimization, in every iteration for every member, we evaluate the fitness function twice, whereas for the other 2 algorithms, particle swarm optimization and differential evolution, it was only once. We want to compare these algorithms with respect to maximum number of fitness function evaluation, whereas the other 2 algorithms, genetic algorithm and artificial bee colony optimization, did not have a deterministic expression for the number of maximum functional evaluation, right. So, for example, in artificial bee colony optimization, depending upon when we encounter the scout phase, the number of fitness function evaluation would change, right. So, it can vary from NP plus 2 NPT, right. So, that is the minimum number of functional evaluation and the maximum number of functional evaluation is NP plus 2 NPT plus T, assuming that the scout phase is encountered in every iteration. Similarly, for genetic algorithm also, the number of maximum functional evaluation is not a deterministic expression. It depends upon whether an offspring undergoes mutation or not. So, for this particular comparison, we are only taking 3 algorithms, because for all the 3 algorithms, we have coded with respect to maximum number of iterations, right. So, if you remember that loop for T is equal to 1 to T, that was there in all 3 of them, right. We did not write it with respect to number of fitness function evaluation, right. So, we can do that, right. So, for example, all the 5 codes we can convert it for maximum number of fitness function evaluation. That only requires a little bit of coding skill. You should be able to do it on your own. We will also upload those codes with respect to the number of fitness function evaluation on the course page. So, for this session we will only restrict with particle swarm optimization, differential evolution and teaching learning based optimization. Right. So, we are not going to change anything in this function file. So, this is the SKS underscore production planning. So, this function file is what gives us the fitness function value, right. So, we are not going to do anything to this function file. Production planning data is just passing the data to this file which evaluates the fitness function, right. And these are the 3 algorithms: teaching learning based optimization, differential evolution and particle swarm optimization. So, all these 3 are now function files, right. So, TLBO returns the best solution at the end of specified number of iteration, the value of the fitness function corresponding to this best solution. So, best sol is actually the set of decision variable, best fitness is the fitness function value of best sol, best fit iter gives the convergence curve. So, it basically tells what is the best fitness function value obtained in every iteration, and that includes the first initial population. This P is the final population. So, the dimension of P would be NP cross D, where NP is the population size and D is the number of decision variable, whereas F would be NP cross 1. So, for each solution in P, we will have a fitness function value. So, that is what is given in F, right. So, the output is same for the 3 algorithm: best sol, best fitness, best fitter, P and F. For TLBO, the input is the fitness function file, the lower bound, the upper bound, population size and the number of iteration, right. For differential evolution, it is the same thing, right. In addition, we need to provide crossover probability as well as the scaling factor. So, this crossover probability is required in crossover operation and the scaling factor is required in the mutation, right. So, similarly for particle swarm optimization, the output from the algorithm is same, right. Input is the problem, the lower and upper bounds, the population size, number of iteration. In addition to that, we need to give the inertia weight and 2 acceleration coefficients, C1 and C2, right. So, now we have these 3 meta heuristic techniques, right, and we have our problem over here, the production planning problem, and this is the data for the production planning problem, right. So, this is a script wherein we are going to compare the 3 algorithms, right. So, the first 3 lines is just to clear the command window, the workspace and close any figure if it is open, right. So here in line 6 we are accessing this function production planning data which contains the data, right. So because we need to provide the upper bound, right, upper bound if you remember it is the H value, right, the maximum production that is possible, right, and the lower bound is 0. Remember it is not the low level value, because if we put it as low level value then we are enforcing an artificial constraint that each process has to be used, right. So that constraint is not part of the problem. The problem specifies that either we can choose not to produce, or if we decide to produce it has to be L or greater than L and it has to be less than H. So there is a domain hole. So that is why we are taking the lower bound as zeros. So this n process will also tell us the number of processes, or in this case the number of decision variable, right. So this is lower bound, this is the upper bound. So prob is a function handle, right. So we are assigning the name of this file SKS underscore production planning, right, to prob, right. And then since we are using 3 algorithms we need to specify the parameters that we are going to use. So we are fixing the population size to be 50 and the number of iterations to be 100, right. So these two values remain constant for all the 3 algorithms, right. In addition to this, for TLBO we do not require any other parameter, whereas for DE we require the crossover probability and scaling factor. So we have fixed the crossover probability to 0.8 and the scaling factor to 0.85, right. And for particle swarm optimization we need to provide the inertia weight, we have taken it as 0.8, the acceleration coefficient C1 and C2 as 1.5, 1.5. So that helps in defining the parameters which are required for the algorithm. So n runs is the number of runs. So for the purpose of demonstration we are just taking 5 runs, right. Let me just remove this, we are not going to use these two. Right. We are going to use this variable best fitness to store the fitness function value reported by every algorithm, right, in each run, right. So we are going to have n runs. So in this case we are going to have 5 runs, right, and we have 3 algorithms. So that is why we have taken 3 columns, right. So what we are basically trying to do is the first column we will use it for TLBO, the second column we will use it for differential evolution, and third column we will use it for particle swarm optimization of this variable fitness. And for each algorithm we are going to run 5 times, right. For each run that we complete we will populate best fitness with the solution obtained from that algorithm, right. So this is the for loop, we are going to compare these 3 algorithms, right, based on 5 runs, right. So that is why we have this loop for I is equal to 1 to n runs, right, and again we are fixing the seed, right. So RNG of I comma twister so that we can reproduce the result, right. And in line 24 we are solving the problem with TLBO, right. So we are giving the necessary input prob, LB, UB, NP and T. So the solution that will be returned by TLBO is all of this thing, the set of decision variable, the fitness function, the convergence curve for that run, the final population and the final fitness function, right. So right now we are interested only in the fitness function value. So we will do statistical analysis based on that fitness function value. So that is why we are not receiving any of these 4 values, right. We are not receiving what is the set of decision variables, we are not receiving the values for plotting the convergence curve, we are not receiving the final population, and we are also not receiving the fitness function values of the final population, right. So if you are interested you can just specify a variable name and then you can appropriately analyze whatever you wish to. So this will help us to solve with TLBO, right. So this line again specifies that, so for differential evolution also we want to control the random numbers, right, so that we can reproduce it. So that is why we are including this line, right. So over here as well as in over here for particle swarm optimization. Even if we remove line 26 and line 29 it is correct, right. Only thing is that we will no longer be able to reproduce the results of a particular run, right. So for example let us say we do not have this, let us say we comment these lines, right, and if we want to reproduce the third run of PSO, only the third run of PSO, it is not possible, right. But if we have these lines over here, right, then we do not need to execute TLBO differential evolution, we can merely say RNG of whichever run was the best run comma twister and we can get those results. So that's why we are fixing the random number for each of the algorithm, right. So similar to TLBO for differential evolution and particle swarm optimization, we are only interested in the fitness function value of the best solution, right. So here we stored it in the first column of best fitness, here we are storing it in the second column, here we are storing it in the third column, right. So the input for differential evolution is problem, its lower bound and its upper bound, the population size, right, the crossover probability and the fitness function. Similarly for particle swarm optimization, these three are with respect to the problem, population size, inertia weight and the 2 acceleration coefficient. For TLBO, we had given only T iterations, right. So here we specify T, but for differential evolution and particle swarm optimization, we are providing the number of iterations as 2 into T. So in this case T we have set as 100 iterations. So we will run TLBO for 100 iterations, but we will execute TLBO for 100 iteration, but for differential evolution and particle swarm optimization we will execute it for 200 iterations, right. So only then the number of fitness function used by TLBO, differential evolution and particle swarm optimization would be identical, right. So remember, we want to compare the results of these three algorithms, but the termination criteria cannot be the number of iterations. Then TLBO will be using more number of fitness function evaluation compared to particle swarm optimization and differential evolution, right. In order to avoid that, we are executing differential evolution as well as particle swarm optimization for twice the number of iterations as compared to teaching learning based optimization, right. So this will complete execution of all the runs, right. So here we have the statistical analysis, right. We are finding the best fitness of all the three algorithms, right. So when we do min of best fitness, it will give us a column vector, right. So the first column of the variable stat, right. So this is just a variable name. We are saying that the first column of the variable stat is the best value obtained by each of the algorithm, right. So stat will have 3 rows, right, and the first column will contain the best objective function value. The second column similarly for all the 3 algorithms will contain the worst fitness function value. Remember, all these 3 algorithms have been written for minimization, right. So this is max of best fitness, and then similar to what we did previously, mean for each algorithm, median for each algorithm, standard deviation for each algorithm, considering the 5 runs which we are executing, right. So let us see what happens if we execute this, right. So here I had kept a breakpoint, right. Let me remove that breakpoint. So it takes a little while to solve. So now we have the result, right. So the first row is for teaching learning based optimization, right. So the best value obtained by TLBO is minus 400 because it is in the first column, right. So the first column gives the best solution with respect to each of the 3 algorithm. The second column gives us the worst solution with respect to each of the 3 algorithm. The third column gives us mean, fourth median, and the fifth one gives us standard deviation, right. So remember our previous discussion that for the current problem, the fitness function will have to have a negative value for the solution to be even feasible. So in this case we can see that differential evolution is not able to obtain any feasible solution, right, because the best solution obtained by differential evolution in all of the 5 runs, right, is a positive value. That means there is some penalty which indicates that the solution is not feasible. With respect to the best solution obtained by the 3 algorithm, the best algorithm is particle swarm optimization because it discovers a solution of minus 546.28, whereas TLBO is able to determine solution which has a fitness of minus 400.59, right. So if one were to implement a production plan, right, they would prefer to choose the solution given by particle swarm optimization, right. So similarly, if we compare the worst value, the worst which is determined by TLBO is better than what is determined by PSO, right. So we can actually look at this best fitness. So these are the results of the 3 run. The first column indicates TLBO, the second column indicates DE, the third column indicates particle swarm optimization, right. So in this case the best value was minus 400.59 and the worst is minus 322.08, whereas the worst in this is minus 285.63, right. Though particle swarm optimization discovers a better solution than teaching learning based optimization for this set of settings, but the standard deviation across the 5 runs of TLBO is less than particle swarm optimization, but the standard deviation of TLBO is less than that of particle swarm optimization, right. Again remember, this set of result is only for this set of parameters, right. So, if we change these parameters of differential evolution, the solution might even improve, right. So, for an arbitrary problem, it is not possible to say what is the best value of PC, F, W, C1 and C2, right. So, when we execute an algorithm, we need to try with multiple values of these tuning parameters, right. Though we have shown you a statistical analysis, right, it is very preliminary, right, because we are also supposed to change this parameters, and then we are also supposed to analyze the impact of these user defined parameters. In this case, we showed you preliminary comparison of these three algorithms, right. So, if we have code of GA and ABC in which we can specify the number of functional evaluation, the algorithm would stop after utilizing that many number of functional evaluation. We can also include them over here. Right now we know how many functional evaluation we took for TLBO, alright. So, that is NP plus 2 NPT, right. So, that value can be calculated and it can be given to that specific code of genetic algorithm and artificial bee colony optimization. So, in that case all the 5 algorithms utilize the same number of fitness function evaluation and a similar statistical analysis can be performed. Right. So, that concludes the comparison of algorithms for this production planning problem. Many times what happens is we want to solve the same problem with a different set of data. For example, in the case study which we are discussing so far, the budget value was 1000 and the raw material 1 that is available was 500, the raw material 2 that was available is 500, right. So, this is what we were having. Let me say this as case 1, right. So, for case 1, the budget that is available is 1000, right, and the raw material 1 that is available is 500 and the raw material 2 that is available is 500, right. So, for this let us say we get some profit, right. So, depending upon which algorithm we are working with, we will get some value of profit over here, right. So, same problem we want to solve, let us say with budget as 1000, right, and the amount of raw material 1 that is available is not 500, but it is 1000, the amount of raw material 2 that is available is also 1000. So, we will get some profit over here. Let us term this profit that we get over here as x1 and the profit that we get over here in case 2 as x2, right. So, if you think about it, here we have only increased the resources, right, some 500 to 1000 we have only increased the resources. So, any solution which is feasible over here is also feasible for this one, right. So, because we are only relaxing the problem, right. So, we should at least get a solution which has a profit of x1. We can get a solution which may have a better profit than x1, but it should not happen that x2 is inferior to x1, because x2 is the solution for a relaxed problem, right. So, similarly for this study we have 2 more cases, right, wherein the budget is increased to 2000, the raw material is at 500, right, and the fourth case is the budget available is 2000 and the raw material that is available is 1000. So, let us call this as profit as x3 and x4, right. So, over here if we see x4 cannot be inferior to any other value, right, because x4 is a relaxed version of any of the other 3 problems. So, any solution which satisfies these 3 cases would also satisfy this. We should not have a solution whose profit is inferior to any of these 3. Now, the question is how do we implement this, right. So, remember for each of this case we need to run multiple times, right, because case 1 is a individual optimization problem, case 2 is an individual optimization problem, similarly case 3 and case 4. So, now we will see how to execute such a problem. Over here if we see, the first figure shows the approach without correction, the second figure shows the approach with correction, right. So, whatever we are discussing holds true for both of them, right. If you look at our implementation, we had those meta-heuristic technique that was sending the value of x and it was receiving the value of f, right, and we had the script file, right. So, through this script file we were passing the algorithm parameter and problem details, right. So, every time what we were getting from the solution of meta-heuristic technique was the best solution, its corresponding objective function, the final population, the fitness function corresponding to the final population and the best fitness function value obtained in every iteration. That was what we used for plotting convergence curve. So, this is what we were receiving from the meta-heuristic technique, right. So, now what we can do is when we pass this problem details, we can also pass the values of budget, the amount of raw material 1, the amount of raw material 2 that is required. So, previously we were only passing the upper bound, lower bound and name of the fitness function file, right. So, this BR1 R2 can be passed to the meta-heuristic technique, right, but this BR1 R2 is actually required in this fitness function, right. So, we will have to now change our meta-heuristic technique, right, to receive this input from the script file, right, and as well as transfer that data to the optimization problem. So, now we will say that what we get from the meta-heuristic technique is x, as well as we will say what are the resources, right. So, this 3 put together, let me call it as a variable RES. So, this RES can be passed to the optimization problem. So, the fitness function which could previously receive only x should now also be capable of receiving RES, right. So, what we are discussing here is more with respect to the implementation, right, and not necessarily with respect to optimization, but since implementation becomes a part of the optimization study, that is why we are discussing it over here. So, this is also true for even if we have correction, right. So, we will have to pass B, R1, R2 every time, right. So, we have 4 sets. So, first time we will pass the first set, second time we will pass the second set. So, that will pass 4 times, and this meta-heuristic technique along with the decision variable will pass the parameters, and those parameters will be utilized in fitness function, and the corrected fitness value and the corrected solution will be returned back to the meta-heuristic technique, right. So, this is one way of doing it. Otherwise, in MATLAB a direct communication can be established between these 2 files, right, using a global variable. So, we will not use that approach. So, this is the file that we were working with, right. So, here let us get rid of things that we do not want. So, we do not want this. Now, we are working only with the correction approach, right. Let me uncomment this, right. So, these are the 4 cases that for the first time we need to pass 1000, 500, 500. For the second time we need to pass 1000, 1000, 1000. For the third time we need to pass this value, and for the fourth time we need to pass this value. So, every case is a row now, right, and we have 4 such problems. So, we will put another loop over here, and now in addition to this we need to pass RES, that is the name of the variable in which we have defined the 4 cases, right. The jth row we need to pass, and all the columns, right. So, these 3 are details with respect to the problem, these 2 are details with respect to the algorithm, right, and again this is a detail with respect to the problem. So, so far we were saying the input to the algorithm is just fitness function, lower bound and upper bound, but we can also pass other parameters, but this will not be used in the algorithm. Since algorithm happens to be in between our script file and the fitness function file, we are passing it to the algorithm, and subsequently the algorithm will pass it on to the fitness function, right. So, over here we have changed the algorithm, right. So, our algorithm is over here. So, this should be capable of receiving that variable, right, and wherever we call the objective function we need to pass this value. So, we call the objective function here, and then over here in the teacher phase and in the student phase, right. So, RES we are not actually using it, right, it is RES, if you see we are not actually using it in the algorithm. So, going back to this problem, right. So, over here we will get RES, right. So, these values are to come from the variable. So, we have written in such a way that the first value contains the budget, right, the second value contains the amount of raw material 1 that is available, and the third value contains the amount of raw material 2 that is available to us. So, now from the script file we can run all these 4 cases. So, now we have defined this outer loop, right. So, this outer loop will take care of the 4 problems that we have, and for each of the problem we need to implement 10 runs, right, and this is the statistical analysis part which we are doing over here, right. So, right now we are not saving the best solution or the values for the convergence curve or the final population, we are only storing the fitness function value, right. So, best fitness E. So, the first time it will be the first column, right. So, instead of this 1 we need to give j, so that we will get 4 columns, right, and we will have 5 rows. So, each row corresponds to a particular run, and each column will correspond to these cases, right. So, for the first case, second case, third case and the fourth case, right. So, if we execute this it will take a little while, right. So, now we have the command prompt. So, we can look at this variable stat, right. So, each row indicates a particular run. So, if we look at best fitness, right. So, these are the 4 cases which we have, right, case 1, case 2, case 3, case 4. So, the first column of best fitness C is case 1. So, for the case 1 we see that the values in phi run are the 5 rows of the first column. Similarly, for the second problem, right, second problem in the sense with a budget of 1000, raw material 1 available being 1000 and the amount of raw material 2 available being 1000. So, these are the results of phi run. Similarly, the third case and the fourth case, right. Now, if we implement a statistical analysis of this, let us say the best value that we obtain is for case 1 is minus 699.38, right. So, that is what is over here, right. So, the first column indicates the best values, because over here if you see stats, the first column indicates the best value, right. So, the third value, this minus 1066.33 corresponds to the best value of the phi runs for case 3 and similarly for case 4, right. The second column of stat indicates the worst value, the third column indicates the mean, the fourth one indicates the median and the fifth one indicates the standard deviation, right. So, here we have shown you only for TLBO, right. So, even in that case we get a table, right. So, what you can do is, in addition to TLBO, you can also run the problem with particle SWAM optimization, differential evolution, genetic algorithm and artificial bee colony optimization. This is how we can run the same problem with different set of data for any number of specified runs with a particular algorithm. With that we will conclude this session. Thank you.